Now you might ask the question, why is it IBM called it smarter cities? Why not just call it smart cities? Reason is, somebody had already taken the name smart. And although we always like to do better than the next chap, it was up for us to call them smarter. Now, what was interesting is kind of how this whole idea of smart cities evolved. Between us here, it really evolved as our marketing team started to look at things like, where does a carrot travel? You say, why do I care about a carrot? Well, it turns out that a lot of carrots travel from the west coast of the US to the east coast, only to be consumed after that prodigious journey. Why? People were asking questions, why do cars spend so much time in traffic waiting to find a place to stop? And so on and so forth. So kind of the problem was stated. The question is, how can we do something about that? And frankly, after 3 years or so working on this, we've got some insights. And the complexity is, we're getting our arms around it. But I would say the bottom line to the problem is, there's so many stovepipe operations that don't use data, and that don't understand the implications of their activities. That results in these problems. So you've seen this chart, says what is a smarter city? That's just one person's view of it. Now the issue is that demand in cities is just growing. Most cities will be full of people close to about, well, today about 80% of the world lives within 200 miles of a coastline. And we've seen all the prodigious numbers that are going to evolve from that. Now, why start now? What's going on right now with cities? Essentially, the issues that we're dealing with, you can read for yourselves. But what we see is increasing demand by increasing density of population. There's just no doubt that most of the rural population is moving to various coastlines. In addition, there's all kinds of challenges that mayors are putting up for themselves to focus on, let me reduce the amount of carbon we emit in this city by 30% by 2030. Prodigious numbers that are actually almost impossible to accomplish without a radical restructuring of the whole infrastructure. But there are ways in which technology, computation, and IT delivered through these systems can help us. Now, let's look at this from a physicist perspective. Physicists like to find the Planck's constant of cities. Let's just look at this briefly. This is Professor Jeffrey West, who has looked at a simple relationship. Now, notice this is log-log, which talks about the log of total wages versus the log of the population. And as you'll see here, the correlation coefficient is not bad, but the gradient is better than 1. It means that the larger the population, the larger the average wage. Similarly, the Planck's constant of cities for this super creativity as measured by a specific number follows a similar relationship. So what's the point here? The point is, the more people you have in a city, the more they interact, the more opportunities evolve, and in general, the better the quality of life. Now, here's an economist view. And what better economist can you find than the economists themselves? Now, I should point out a couple of things which you can't read any of this, I'm sure you get them in the charts. But this was sponsored by Citigroup, and one of the contributors to this was the mayor of New York City. And hence, we have an interesting overall score. Let me read you. The scores go from overall score, economic strength, physical capital, financial maturity, and institutional effectiveness. I've missed one thing here. The overall score, London, New York, London, Singapore, Paris, Hong Kong, Zurich, Vancouver is about 18th. That's the first place I see. Oh, sorry, Toronto ahead. If you look at the physical capital, Vancouver is right at the top of the list. And you'll be able to read this yourself. But the point is that these cities are attractive because of a number of reasons. First of all, their ability to attract capital. Physical, economic, and intellectual capital. There's also this middle tier that's growing. And the most significant advantage is their ability to attract talent. If you provide an environment that, for example, makes it easy to get over your transportation route, if you provide an environment where it's easy to do business with the government, these are simple things, yet they contribute to this overall quality of life. Interestingly, African and Latin American cities lag most in terms of competitiveness. Brazil is clearly making big efforts, but as you can see, the ratings show where they are on this overall list. Increasingly, this is a study IBM did, and the x-axis is the third level of education, this primary, secondary, and tertiary level, as a percentage of labor force. And if you look on this axis, it talks about knowledge-intensive services, basically showing that there's a big shift to the knowledge-intensive services as a percentage of the labor force. It's basically saying economies are becoming more knowledge-intensive. So, let me point out one way in which we've looked at cities. When you look at a city, you say, what does a city do? How does it behave? How can you possibly structurally look at a city? Well, this is the way we've looked at it. After these, a number of experiments, it became clear. In a city, you have infrastructure. Roads, pipes, wires, buildings. And the objective with respect to those systems is fix, repair, renew most efficiently. Essentially, what you're trying to do is optimize the prediction of what's going to go wrong, the location of where it's going to go wrong, and how to assess resources to fix it. That's a mathematical objective. Secondly, if you look at resources like electricity, the objective is to match supply to demand. In New York State today, the way in which they match electricity supply to demand is simple. They have the independent system operator in Albany. They have a big building that's almost impossible to get into, which you'll understand why in a minute. And what they do is they have a number of people that assess what they think the demand is going to be, and they go to the generators and say, Joe, how many kilowatt hours can you give me? How many millicents per 1,000 kilowatt hours, which is an exaggeration. But they're asked what price they have for what rating. And they fill the bucket up from the lowest price to the highest price. But they use historical data to do that. If you could only understand what people wanted to do, if you could find ways to get that understanding and influence that understanding, you could be a lot more efficient. And again, the objective there is to match supply and demand. That's another mathematical function. Finally, there are the people. If you don't have people, you don't have a city. The people cause the demand. The people cause the interaction. And so if one could gather insights from people, not just by simple Twitter feeds or online work that they have to do, through ways in which you observe their behavior. For example, we did an experiment in the Pacific Northwest here. As part of that experiment, we had about 200 houses, and each house had a thermostat. And each thermostat had settings which said maximum savings all the way through maximum comfort. So we set up a whole function where each thermostat would bid into an electronic marketplace and buy electricity from a certain kind of contract to fulfill their desires. So based on a sort of simple interface which transformed a complex bidding and acquisition process, we were able to understand exactly how people wanted to trade comfort, like 5 degrees hotter in the summer and 5 degrees colder in the winter, versus what they would pay. So it's not just about gathering Facebook or Twitter feeds. It's really not about that. It's about finding ways in which you can address what people do without interrupting what they do. So we've got a number of projects around the world. I'd like to speak to a few of them. Before I speak to them, here's kind of the bottom line. Cities really waste a lot of resources because, frankly, they don't have a method to understand how well those resources are being used. And even worse, they don't have a method by which they understand how the guys that are digging up the road to repair the road are working with the guys that are digging up the road to repair the water infrastructure. Simple issues like that. We'll show you experiments that we're doing in Minneapolis to deal with this. One of the things, when IBM went out and said to cities, hey cities, and you had one here, tell us what your biggest problem is and we'll send 4 or 5 of our smart people to work on that problem for you for free for a month. I would ask anybody in the audience, what do you think the biggest response was? What did cities really want? Anybody want to tell us? Do not be afraid.
Traffic.
Traffic. What else?
Garbage.
Garbage. What else? Security. Budget. Taxes. Anything else? What was that? Education. Answer is no. What cities wanted to do was to communicate with the denizens. The primary objective of the city management was, how do I get the message over what I'm trying to do so that I can get feedback from the denizens to tell me what I'm doing right? You know, if you think about it, you're sort of being elected on a cycle. You really need that kind of feedback. That's pretty good. The efficiency drives discovery of data. Once you have people sitting down looking at a problem with the data, then at least there are chances of people twisting ideas around and changing opinion into analysis is much greater. And I'll show you examples of that. Cities do see the value of predictive models. You know, what's interesting is you'll hear this whole discussion about cities should publish their data. And we'll build a whole business out of the data that cities publish. Maybe. Our experience is cities start off that way, and then they say, whoa, wait a minute. I'm creating a whole new service here that I've got to pay for. How am I going to make money out of it myself? Right. It's a big challenge. In fact, we have a lab in Ireland, Dublin, where we're investing about 100 people to work just on smarter cities, where we have an extremely tight relationship with the city. In the discussion of how to deal with that data, we've learned a number of things. At the beginning, the data is shoveled out there to comply with freedom of information, because that's the simplest way to comply with it, is just shove it out there. The second thing is, hey, if you start building businesses on that data, which was initially open, how do those businesses take advantage of data and have a competitive advantage against that data? A whole set of questions. And then, of course, privacy, a huge issue. And so we're taking small steps at a time to understand what's private, how to publish the data, what data to make available. It's not a simple issue. The other thing is, if you think about how the whole city system works, let me give you an example of a kind of a complex issue. If I am a developer, let's say I'm the Ratner Corporation in New York City, and I want to improve the performance, the energy performance of my buildings, what do? I go to a bank and I say, hey Fred, can you lend me $10 million to improve the energy performance of my buildings? And Fred says, yeah, Joe, yeah, sure, but how much are you going to improve it? And Fred says, 20%. Joe says, how do I know you can do that? Where are the metrics that prove to me that that happens? Where is the professional analysis that I can rely on, just as I can from underwriters' labs? There's no such community. So you'll say, okay, I'll give you half of what you're asking. In addition, once that loan is made, there's no way to easily convert that into a derivative or build a financial business across that. And we're just talking about one small thing, a developer wanting to improve the energy management in buildings. If you look at further down the line, how does a planner and architect talk together? How do they convey their ideas? They do that in very structured ways. Yet there's a lot of information that's not conveyed that can make things much better. Let me take this to the limit. Imagine that we have a whole development system here where from the beginning of the business development, the business, you know exactly what the value is of that building. So you put a building in downtown Edmonton, and based upon that building, you not only know how many people will use it, how much energy it will use, but you will also know how many planes are going to land at that airport, and how many cows are going to be killed to fill the trays for the food on the plane in the airport. It should be possible to connect these pieces together so that one has a holistic view of the city. Today, when you build a building, and you say it's LEED, in the US, for example, an energy rating LEED Platinum, how do you know it is? Well, you know because it's how you built it. But how do you know whether it maintains its performance? There's no way to do that. How do architects verify that a building behaves in the way that they say it does? Anecdotally. Today, if you, for example, build a chip, you build a chip with tools that allow you to not only design it, but to verify it before it's actually operational. There's no such thing to verify cities. It's all done rule of thumb, best practices. We need to move away from these anecdotal and sometimes actually very effective rules of thumb and best practices to quantifiable systems that allow us to do the measurement. Okay, so we started off thinking about the smarter city from individual small processes, perhaps managed by paper, all the way through cities where there's a central place, whether virtual or not, where you can say, I'm going to get a certain storm of a certain kind at a certain day. How much water is that going to generate in this location in the city? How much energy am I going to have to use to pump that water? And if I reroute traffic and change the routing of the subways and manage the pumps, can I reduce the overall energy usage? That's where we think it's going. And I'll tell you the first place it's happening where emergencies happen. The only time city agencies get together really is when the fecal matter hits the rotating oscillator. And that's because the sense of urgency provides the motivation for people to just break down their barriers, go across processes, and get the job done. Yet that's the place, and I'll show you the work we did in Brazil, in Rio, where this integrated view of a city evolves from. So why models? Essentially, models because we can predict from those models. People don't want to see just how much energy is each building used in a city. People want to know what will happen if I do X, Y, and Z. What if I cover the tops of these skyscrapers with photovoltaic systems? What if I feed in renewable energy from wind? What will happen to the overall peaks? So from data, you can create models which give us insight. And you know, it's interesting to see what's been happening over the years. You started off with this idea of standard reporting that says what's happened, going through forecasting, what if trends continue, and then optimization. Once you have a model of a system, you can say, what if I do this, and can I, for example, run my city traffic for minimum carbon emission? This is where the analytics landscape is evolving. Some example of these systems in asset management. Remember those, we had those three boxes: infrastructure, resources, and people. Well, the infrastructure, the assets, what you want to optimize is how you repair systems. We talked about resource optimization, about power, and people. And in data and analytics, data comes from many, many different places today. And you'd be surprised at the kinds of places you can get data from and do pretty deep analytics on it. The kinds of analytics can be many varied: statistical, data mining, classification, discrete event. There's many kinds of analytics we can apply against the problem, and I'll show you some of them. And I should also say, you know, models are really the abstractions of reality. It's important not to get involved in the thought that this model will solve every problem. It's important to apply the right model to the right problem. There's many different kinds, but really modeling is a trade-off. Right? I won't bother much with this. This is just, we'll show you some examples. If there's just one thing I'm going to ask you to remember from this whole presentation, it's that to bet on the Horton. It's that the data enables you to create models that allows you to drive optimization and make business decisions. From those decisions, you get answers which give you more data. This is what makes cities smarter. Give me the data so I can build the models that I can predict and make business decisions. Here's an interesting problem. There's a company called Walker's Potato Crisps in England that decided they wanted to see where all the carbon emission came from in their process. So they talked to the farmer, they talked to the producers of the sunflower oil, the corrugated cardboard. They went through this in minute detail. And they found the farmer was using 44%, Walker's in cutting and frying and processing is 30%, then 26% in packaging and distribution. What they didn't know was the farmer was soaking the potatoes in water, and Walker's was having to boil that water off. Why? Because the farmer was selling potatoes by the pound, by the kilo. And these kinds of disconnects happen everywhere. In cities, for example, those building owners, they don't give a pig's burp about how much energy buildings are used because it's the tenants that pay for the energy. You need to connect the different pieces together to make these systems work. So our first models. We had a lady called Laura Winter that went to Singapore, and in Singapore they track their tolls very carefully. Where you are, what you're driving, and when you're there, determine how much you pay. So they've got a lot of data about the traffic. And based upon that data, we were able to build a statistical model. This shows the forecast of the traffic volume. The black shows the actual, and the forecast is made an hour ahead of the actual. And then this is an incident. The point was, we used statistical models to create this prediction tool, which is now going to be used to monitor traffic and predict it in New Jersey. In addition, what's happening around the world, this is from our team in China, there's a big demand to understand multimodal traffic. That is, if I get on a bullet train, and then from the bullet train I get to a subway, and from the subway I get to a taxi, how do I manage the traffic across that whole system? How do I do that most efficiently? So here's, for example, what we've built is a fairly complex simulator for the system. So part of that also involves building models, agent-based models, that you've seen this kind of thing before, I'm sure, that enable you to understand where people are actually going to go. So each agent has an average speed, each agent has the distance, the closest distance they will approach another, and so forth. And we just launched these agents. Now, if architects would use these kinds of agents to design buildings, they'd have a much better understanding of some of the issues that they've never thought about. And in fact, today many architects are beginning to use that. We're using agent-based models to help figure out which roads to optimize, which roads to put in place. And in addition, what this simulation is doing in China is they are taking data from the engines of the individual cars themselves. They're taking data from two-way GPS. They're looking at all kinds of aspects of public and private transportation to understand what would happen if I did change the timing on traffic lights, move the direction of traffic, and also looking at the behavior of the engines themselves. In buildings, this is a piece of work a lady called Jane Snowden did in our group. Our challenge, actually, when you start working with cities, one of the biggest challenges is when you say to a city, I want to do an experiment with you. They send you to their procurement office. Right? How the hell is procurement going to know what to do about an experiment? And if I say one thing to cities, if you want companies to work with you, we need to find a way around this. Well, the way in which we find the way around this in New York was through the universities. Universities are an incredibly good channel for companies to work with as we go and engage with cities. So for example, we've got this group working in New York City on the Center for Urban Science and Progress, which works through NYU. We're working with Cisco and various other companies to build this idea of smarter cities education and engineering. So what we did in New York City was we took data from 1,500 schools, I think it was, maybe it was 1,200 schools. Now, you can imagine, what do you have from these schools? Well, we've got data that shows bills every month. Got gas bills, oil bills, coal bills, steam bills, you got bills up the kazoo, right? And now you've got to analyze these 1,200 schools to try and understand what's going on with them. Actually, at the same time we were doing this experiment, we did a much more granular experiment with I think it was McMaster University, where McMaster provided data on a sort of 15-minute basis as opposed to a monthly basis. So what did we learn? I'm not going to spend much time here. We built an inverse model. Actually, I'll spend a little time here. What we're trying to do with this particular model is look at the characteristics of the building. Their age, occupancy, number, density, the consumption, and basically by measuring the amount of heat used, we could build an inverse model which gave us kind of a lump model for the building. What does that really help you with? It really says if you change the building to have these particular characteristics, you could change how much energy you would use and you could predict it. Wait, sorry. So here's some examples. We took this data from those schools and plotted it against a monthly trend. This is just from one school, but we've got 1,200 schools as a database. And then sort of plotted out the school usage on a chart. This is just one example. You can do many different queries to the database. What we found was that we first of all clustered schools. That's the first thing you do in statistical analysis. You look to see which schools have the same age. You look to see which schools have the same square footage. You look to see which schools have the same characteristics. So put them all together and compare them. Well, one of the first things we found was there was a number of deviations. We'd find two schools that were using maybe 30–40% difference in energy. Why was that? Believe it or not, simply because one school had double glazing, the other had none. You'd think that somebody would know this, but it's not known. I mean, it's known, but it's not cataloged. It's not analyzed. This is such low-hanging fruit around us in cities that, like I said, I think it's easy to say between 10 and 50% of the resources that we use. This is just one example. It's a simple statistical analysis of a lot of data. So in Dubuque, IBM had engaged Dubuque because we built a data center there, and then the mayor and the city, which had once been a city that built furniture, it was very wood-centered, they were now building cities, they were now trying to build a green city. Ultimately, what we did with this city was try to understand how we could reduce their energy usage by behavior. So what we did was we broke the city up into groups of 50 families. Each family could see their own individual water usage, it was in this case, individually, but they could only see the average energy and average water use for each group of 50. So for the first test, we had 5 groups of 50, and they would compete with each other to try and figure out what on earth they could do to reduce their overall water usage. Over a period of time, we found significantly reduced water usage for those who really wanted to do that, maybe 10%, 15%. And so this approach of competition, again, not rocket science, seems to have worked pretty well to try to reduce the water usage. These are some of the outcomes, but I've just already pretty much stated to you. However, we did another one, which is underway right now, with energy. Now, there's no shortage of water in Dubuque, but when you start talking energy, this is real money. And they conserved, to date, this has been going on for about 6 months, about 11% of their overall consumption. And in fact, with this particular process, we showed them how to conserve it based upon their patterns of usage. Finally, in Rio, it was an interesting situation. We sent a group of people to Rio to talk to the city. And we sat down with them, and the mayor came over to one of my friends, Guru Banavar. And he said, Guru, I've got a problem. And Guru says, well, what's the problem? He says, when I get a flood, the water comes down the mountains, hits the favelas, and people die. The mayor said, I just started here as mayor. I spent some of my time in Connecticut, as it happens. And the mayor said to himself, says, Guru, I asked myself, what the hell do I do? As this rain's coming down in torrents, what do I do? And he said, the only thing I could think of was, what do we do in Connecticut when there's a storm? And the only storm we could think of was snowstorms, of which there are not too many in Rio, as I understand. And he said, they say stay home. So that's all he could do. He could just tell people to stay home. So Guru turned to us and said, look, we've been working on weather prediction for a long period of time. We had a gentleman join IBM Research 25 years ago. We knew he was good at what he was doing, but we couldn't figure out a business for weather. Actually, it turns out the business of weather is business. Pizza companies sell 30% more pizza when it rains and double their sales when there's a storm. Why? Because they deliver. I mean, not rocket science. But being able to stage the goods and predict is very important. So what we did in Rio, instead of selling pizza, we built a high-resolution weather forecasting model. It resolves down to about 2 square kilometers on a side. We can tell you what the weather is within that one region. Based upon that weather, what we do is we provide a model of flooding, which gives you the precipitation estimates. And from that, you can then decide what to do. Where the rain is going to be, where the flooding is going to be. And then you can build this overall emergency management center, which is what they did, where they bring in the police, the traffic, the emergency management crews, and they provide this predictive analytics that helps them decide where to put the resources at what time. I hope I've just given you a quick glance over the issues of smarter cities. They're not simple. There's a lot of low-hanging fruit because agencies don't work together. There's a lot of low-hanging fruit because there's no data taken and analyzed. But it's the modeling that's going to help us move forward. And this idea that cities as a domain, where a pedagogic domain, in fact, where we bring the architects, the developers, the engineers, and the road transportation engineers, the emergency management crews together to build an understanding of how cities work, to create a discipline around this topic, and to actually create business for cities. That's a big opportunity. And most cities are just beginning to realize this. As I mentioned, New York City, the mayor had asked a number of colleges and universities to submit proposals for a center for advanced engineering. One of those centers was focused very much on this engineering around cities. This is just beginning. It might be a thought for other cities to do. With that, let me say thank you for your attention.